Hi, this is the beginning of chapter 16, and 16 is all about acids and bases and their identification. First thing is the definitions of acids and bases, and the first definition is the Arrhenius definition, and that's for acids and bases that are aqueous solutions. An acid is a substance when dissolved in water increases the concentration of the hydrogen ion. An acid always has hydrogen ions in it. And we typically say that it is an ionizable hydrogen. And so because it's considered to have an ionizable hydrogen ion, we indicate it most of the time with the hydrogen out in front of the anion, but not always. Okay, so when we have HCl, it's going to dissolve in water and it's going to form hydrogen ions and chloride ions. So the difference between the acid and the base is that the base increases the concentration of the hydroxide ion. So here's a classic base, sodium hydroxide dissolved in water. It's going to turn into two separate ions. And then there's a second definition of acids and bases called the Bronsted-Lowry definition. And this is a little bit different in that an acid is a substance that donates a hydrogen ion. Bronsted-Lowry acid and acid is really the same definition as the Arrhenius. But where the difference is in the base definition. A base is anything that can accept a hydrogen, so it accepts a hydrogen, whereas for the Arrhenius acid, it had to have the hydroxide ion. Bronsted-Lowry base does not. So if we look at the Bronsted-Lowry acid, very similar to the Arrhenius acid, and you'll see here that I've introduced this hydronium ion. There's a couple of ways of illustrating how an acid ionizes, and you can show its actual reaction with the water, or you can just abbreviate it and show that the hydrogen ion has ionized. So all that's happened here is that the hydrochloric acid has given up its hydrogen to the water, and in turn, it forms this hydronium ion. So some resources will talk about the level of hydronium ion in the acid solution or base solution, and some resources will just talk about as the hydrogen ion. They mean the same thing. Well, one is an illustration of how the hydrogen actually connects to the water molecule. So then the Bronsted-Lowry base is a little different. So this is the base, it's ammonia. And this base doesn't have hydroxide in it, but it reacts with water and it forms a hydroxide ion. So as long as it can increase the hydroxide ion concentration, it's similar to the Arrhenius acid, but it doesn't have to have the hydroxide ion in it. Okay, so we also talk about amphiprotic substances, and these are substances that can be Bronsted-Lowry acid and base. It can have behavior of both. So, for example, water is an amphiprotic substance. As a base, okay, other way. So as a base, water can react with hydrochloric acid to produce the chloride ion and the hydronium ion. So in this scenario, the HCl acts like the acid and the water acts like a base. And then here's H2O behaving as an acid according to the Bronsted-Lowry, because the acid will donate a hydrogen ion. And so here's what happens in this scenario. The ammonia acts like a base, the water acts like an acid. And that's how we end up with the hydroxide ion in solution. And so we call these conjugate acid-base pairs. So if I take, for an example here, this acid is nitrous acid, and react it with water, put it in water, this reaction occurs. And so this is my acid. In this pair, the water acts as the base, and then once the acid gives up its hydrogen ion to form the hydronium ion, it's going to now switch character on the product side. So what happens is that the NO2 ion that's left behind acts like a base, and the hydronium ion that was formed acts like an acid. So what we say is that the NO2 ion is the conjugate base of the acid. And then we would say that the H3O positive is the conjugate acid of the base. So that's how we would identify conjugate acid-base pairs. But oftentimes we would look at, if we're not, necessarily interested in identifying them as conjugate acid-base pairs, we might just show this ionization of this acid like this. And this has double arrows, and we're going to see these double arrows as we move on a little bit further, but you use double arrows to indicate a weak acid or weak base. Okay, so then here's another example where we have conjugate acid-base pairs. Here's ammonia, that's my base. Why am I calling this acid, this water acid? Because what happens is that it gives up one of its hydrogens to the NH3 to form the NH4 positive ion, and leaving behind the OH. So what we say then is that NH4 is the conjugate acid of the base, and we say that the OH is the conjugate base of the acid. So what's left behind is the conjugate. Okay, and then here I just have a little example that you can try.